you are okay. Just I'm going to continue and give you, let's say, a slight idea about the Euler formula, okay, and the Moivre formula because it's very helpful and very, let's say, important to work with, okay. Just I'm going to wait for you till you will join, okay. This is the pioneers in mathematics, okay. Murad Sultan Ezouidi, okay, is now looking for continuing the revision for you, okay. Let's say you have Wi-Fi problems. I wish the problem will be solved, okay. So as usual, you are going to join your lecture and watch the method of Euler formula and Euler's identity, okay, and what else, and the Moivre formula because it's very important, okay. I wish that it will be clear for you how can you work with, okay. I want to first of all cut this brand folder, new brand, I will see, new brand now, okay, active, okay, upload new, I went to, okay, so whatsoever will start. I will share now my screen, okay, select window. I want to make here, let's say, the entire, okay, the entire screen. I want now to fix it as possible as I can. No, it does not fix it, okay. Chrome table, I'll see, no, it doesn't work this one. So, okay, share. I'll see how it will come, okay. Now, learners, we continue. We call that this is now this is our lecture about let's say Euler formula identity and the Moivre formula. Okay, so okay. Now, learners, it's let's say 38 past 12 a.m. Now the question is that Euler's formula tells us, in fact, that a exponential ix equal cosine of x plus I sine of x, whatever be the x here, it's a real number. Okay, in this formula, we told that in this formula, ax means e to the power ax or e to the power I all to the power x. Okay, it can be written as cosine x plus I sine x. Okay, this one it's called the Ellers formula or the formula of Ellers. Just wait for me, bro. Give me 10 minutes, okay? So therefore we told that x is a real number, okay? And E here it's called the base of Euler base, okay, or is the base of the natural logarithm. Approximately it's 2.718. Okay, and I here, this I, okay, that is written as an index, is the imaginary unit, okay, or square root of -1, because -1, there is no real numbers that will be equal to root of -1, but here we consider it as the imaginary part. So in fact, we can say that Euler formula, the formula of Euler, establishes the relationship between trigonometric function and exponential function. Okay, it's a good relationship between we call the trig function and the exponential function. This formula, learners, can be taught of geometrically as well as relating to representation of the same complex number, okay, of the same complex number plane. Therefore, learners, the following are some key values in Euler's formula that correspond to important point on the unit circle. For example, if we suppose that x equals 0, we will get the exponential of 0 equal cosine of 0, which is equal to 1, plus I sine of 0 is 0. Therefore, 1 plus 0 is equal to 1, which results, in fact, in 1 equal 1. We know now that the angle or the argument here of the complex number z and the unit circle is equal to 1 on the real axis. And if we suppose that now we are going to change or give another real numbers x is equal to 1, therefore we'll get e to the power I1. Just one moment, bruh, I need you. Okay, we told that exponential to the power I is cosine of 1 plus I multiplied by sine of 1. And this suggested that a exponential of I is the point on the unit circle, okay, with an angle of 1 radius, okay. If you want to change the radius, you will just, let's say, multiply this radius degree, multiply by 180 degree over pi, okay. If we suppose now the learns that x equal pi over 2, we'll get exponential of I pi over 2 equal cosine of pi over 2, and cosine of pi over 2 is 0, therefore plus I sine pi over 2, and sine of pi over 2 in fact is equal to 1, therefore it gives me the imaginary part. So the result is frequently applied in general in physics. Now if we suppose that x is equal to pi radians, we have e exponential I pi equal cosine of pi, which is minus 1, plus I sine of pi, which is equal to 0. Therefore, minus 1 plus 0 is minus 1. This, you see, this one exponential I pi equal minus 1, or exponential of I pi plus 1 equals 0. It's called the Euler identity. Okay, this is the Euler identity. Okay, it derives from, let's say, Ellers formula when x equal pi. Okay, this is the Euler formula. Okay, this is, it's very important, and it's a particular, let's say, uh, formula here. Okay, and just here, if x equal pi, exponential I pi equal cosine pi minus 1, so it will be exponential of I pi plus 1 equals 0. This is the identity of Euler. Okay, now learners, we move to the next part. At least you got the point how the formula of Euler is given, and how when x equal pi you will get the Euler identity. Okay, now we move to the next part, which is very important. Okay, this is the Euler identity, means that you are going to work with the unit circle. Okay, and here is the point created by exponential, let's say, I pi, where our discussion begin, in fact, as that. Exponential I pi, it's written as, it results to negative 1, can be rearranged into this unit circle, okay, and it can be rearranged as, in fact, exponential of I pi plus 1 equals 0, okay. This is the famous Euler identity, okay. Now, learners, this is the unit circle. You see, this is the unit circle. This is 1. This is I, the imaginary part. This is the axis. This axis denotes the real part, and this is the imaginary part. Therefore, this is 1, and this is minus 1 in the real part of any complex number z. And of course, that has a modulus of 1. And this one is the imaginary part, I and minus I, okay, of any complex number where its modulus is equal to 1. So this is how can you understand the meaning of Euler's identity. Now let's work with this kind of a question formula, Euler formula for complex numbers. We can create, let's say, therefore, the formula of the Moivre, okay, with some help for Linohard Euler, okay, means the here we can say that Euler formula for complex numbers says that a exponential x equal cosine of x plus I sine of x. And the exponent laws here tells us that exponential I theta or exponential of argument of any complex number z all raised to the power n, it just you are going to multiply the powers. It will be exponential I and theta or I and argument of z. So now if we are going to replace exponential I theta by, let's say, the polar form cosine theta plus I sine theta, we'll get, and we will try to show that exponential I and theta equal cosine and theta plus I sine and theta. Okay, this is general formula for the Moivre formula. Okay, for example, in the final exam, if z equal, for example, 1 plus I, and the question is looking for you to find z to the power 16. So you are going to apply this formula. Means you should first find the modulus of 1 uh, plus I, which is root of 2, and the angle is pi over 4. Therefore, to the power 16 means you are going to write root of 2 to the power 16 exponential of 16 multiplied by pi over 4, which is 4 pi, and 4 pi is 1, therefore it will be root of 2 all to the power 16. Okay, now learners, this formula, a exponential I and theta, is in fact equal to uh, cosine and theta plus I sine of theta y, simply because exponential of I theta is equal to cosine theta plus I sine theta, and exponential of I theta all to the power raised to the power n, just you are going to multiply n by the argument of the complex number, and n by theta, means equal cosine and theta plus I sine and theta. Okay, and here also, if also this is including what exactly? Including the radius or the modulus of the complex number z. Means this is my complex number z equal r cosine theta plus I sine theta raised to the power n. Therefore, it will be r to the power n. Okay. Uh, Times cosine and theta plus I sine and theta, then close your parentheses. Okay, this formula, the last one, it's called learner's cosine. It's called, let's say, the formula of de Moivre. Okay, so now learners, just a quick review for the next. Okay, just I'm going. Okay. Now, learners, if we are going to see, for example, z is I to the power 3, I to the power 2, and so on. Okay. I will just show you how it works. You see this one? So this is exponential of 0i, which is equal to 1, exponential of, let's say, uh, 2 pi over 2i is equal to minus 1. And you see this angle, how it works. The complex z, let's say, is lying on the circumference of the unit circle whatsoever, let's say, the power, okay, of my exponential of the Euler identity. Let's say it gives me numbers between minus 1 and 1, and this is the exponential of I equal cosine of 1 plus I sine of 1. Okay, so now learners, I will just move to the next part. We told that here is this question. I already explained it. I already explained this. but I'm going also to make it clear for you. Okay, here you can see that. Okay, you can see that Z1 a complex number such that the modulus of Z1 equal 1. Okay, and the argument of Z1 is 2 pi over 3. Therefore, the question, try to write Z1 in terms of, in the form, polar form, okay, x plus iy. So therefore, my complex number here in general is r exponential I argument of the complex number Z1. And R, in fact, is the modulus of the complex number Z1 times exponential I argument of Z1. But you can see that the argument of Z1 is 2 pi over 3. You should use the exponential form and change the argument of Z by 2 pi over 3, and the modulus is 1. So 1 multiplied by exponential of I to the power 3 is equal exponential I to the power 3 to the power I multiplied by 2 pi over 3. This is polar form, learners. I will change to, okay, this is polar form, okay, polar form, polar form. I will change to what? Okay, I will try to change this to, okay, to, okay, this is called exponential form. Okay, exponential form. I'm going to change it to exactly polar form, polar, polar form. Okay, to change this, you are going to use what exactly? To use this formula that we told that should be, you should at least know about, which is Euler formula. Okay, then you will apply the Moivre formula. Therefore, exponential 2 pi over 3 learners is equal cosine 2 pi over 3. This is 1 multiplied by cosine 2 pi over 3. It will be cosine 2 pi over 3 plus I sine 2 pi over 3. This is the polar form, and this one is the exponential form. But here you can change, let's say, convert 2 pi over 3 radians into degree. Okay, so you can see that 2 pi over 3 in fact is 120 degree. Therefore, the complex number z is cosine 120 degree plus I sine 120 degree. And let's say 120 degree is an angle that lies on the second quadrant. So cosine is negative and sine should be positive. Okay, therefore cosine of 120 degree learners is negative half, and sine of 120 degree is root of 3 divided by 2. Therefore, this polar form I will write as x plus iy, means x is in fact negative half and y is root of 3 divided by 2. Therefore, in fact, I wrote my complex number is that. Okay, if one learner asked, Sir, who told me that this one really, let's say, denotes the complex number Z1? Okay, here you are going to just calculate the modulus of this complex number that is written in its polar form, okay, or rectangular form, okay. You should calculate the modulus of this complex number Z1 and you should find the value equal 1. Then the second step, we should find the argument of this complex number z1 minus half plus root of 3 divided by 2i, and the argument should be proved or appeared or written as 2 pi over 3. Let's first of all learn do as the following. So this is the complex number z1, isn't it? Okay, therefore I will write here z1. As a conclusion, I will write this as z1. Okay, as z1. Sorry, I will go back like that. This is my complex number. Okay, this is my complex number Z1. Okay, this is, therefore I will write here, therefore, okay, the complex number Z is equal to this. Okay, now I will try to calculate the modulus of Z1, which is root of negative half squared plus root of 3 all divided by 2 all squared, means Z1, the modulus now is negative half all squared plus root of 3 divided by 2 all squared. 1 squared minus 1 squared is 1, 2 squared is 4, root of 3 squared is 3, 2 squared is 4, then 1 plus 4, 3 is 4, divided by 4, 4 divided by 4 is 1, therefore root of 1 is equal to 1. Therefore, in fact, I appeared that Z1, the modulus, okay, for this complex number is equal to this one, okay, equal to 1. Therefore, you don't have problems about this modulus number. Now you are going to write to find, let's say, the argument of this complex number Z1. Okay, I'll just okay. So I will make like that, learners. Okay, I erase it maybe. Okay, no problem. Okay, then it's clear that yes, here this is the real part. Okay, this is the real part. Okay, this real part of z. This is the imaginary part. This is negative half, and this is root of 3 divided by 2. Therefore, learners, there is an angle here from the real positive axis of z, okay, connecting the terminal side of the angle. This is a theta, and this is argument of z. You can see that this angle measures 180 minus 60. Theta is equal 60. Therefore, 120 degree you can convert to pi over 3. So I will just write now argument of z is 2 pi over 3. So this is your complex number z is already written. For the second one, the question is find the argument of z1 to the power 3. Here, so z1 is minus half plus root of 3 divided by 2. If you are going to, let's say, raise it to the power 3, you should use the expansion, the binomial expansion to the power 3. Means a plus b to the power 3 is a to the power 3 plus 3a squared b to the power 1 plus 3ab squared plus b squared. And then you are going to simplify where possible, and you should appear that in fact is equal to 1. Therefore, the first method here, learners, I will try to use use the first formula, argument of the complex number z1 to the power 3. This power 3, learners, will come in front of the argument. It will be 3 argument of z1. But in the exercises, argument of z1 is 2 pi over 3. Therefore, I will make 3 multiply by 2 pi over 3. Then I will simplify by 3 above and down the main division. It remains only 2 pi. Therefore, the argument of z to the power 3, in fact, is 2 pi. And let's say the complex number z1 to the power 3 should be equal to 1. Okay. And now note that this is a formula. Note that argument of z1 to the power n is equal to n argument of z1. Means whatsoever this is, argument of z1 to the power 2 is equal to 2 times argument of z1. Okay, the second method, I will use this one. I will just suppose that z1 is exponential to the 2 pi over 3. Then I should erase this one, raise this to the power 3. Means z1 to the power 3 is equal to exponential I to pi over 3, all raised to the power 3, like that. And 3 here and 3 here will be cancelled out. So it will be exponential I to pi only. Okay, or you can, let's say, multiply 2 by 3. It will be exponential 6 pi divided by 3. Then divide both sides, both the numerator and the denominator, by the common factor at 3. It will be exponential I to pi, and exponential I to pi is equal to cosine 2 pi plus I sine 2 pi. Sine 2 pi is 0 and cosine 2 pi is 1. Therefore, this one should be equal to 1. Therefore, 3 argument of z1 will give 2 pi exactly. For the second method, okay, for the second method, learners, I'll just proceed like that. We have z1 equal, okay, exponential equal cosine 2 pi over 3 plus I sine 2 pi over 3. Therefore, I should raise this to the power 3. I will use what? I will use the de Moivre formula, means cosine ix to the power n is equal sorry, exponential ix to the power n is equal to cosine an x plus I sine an x, means cosine 2 pi over 3 plus I sine 2 pi over 3, all raised to the power 3. This 3 should be multiplied by the